Okay, let's talk about polynomials. And polynomials are such a huge topic in algebra and in mathematics, but oftentimes, we study polynomials, through the years. You probably don't even realize it, and you may not even, understand the big picture because you've been learning these little things. So what I want to do in this video is really kind of review some of the big picture concepts. So we really make sure we understand the big ideas behind polynomials. Again, polynomials are the kind of building blocks of what you learn in algebra and more advanced mathematics. So things like 2x is a monomial and 2x plus 7 is a binomial. And you learn all kinds of things about polynomials, like how to factor them and solve equations with them, etc. But I'm going to kind of get into even bigger picture concepts about polynomials that really start, at the basic levels of algebra and continue on into, advanced mathematics like calculus. So I'm just going to kind of review some big picture ideas. Now, you may not have learned some of these things yet, depending on where you're at in your education. So if you're in, let's say, Algebra 1, you may not have gotten to some of these more advanced concepts, but you could still, learn what I'm going to, get some value of what I'm going to be talking about here. I'm not going to be getting into the details of all these advanced concepts. I'm just going to hit some highlights of polynomials, and polynomials are outstanding little things in mathematics. They are excellent to work with, and again, they have extreme importance in mathematics. That's why we really study them in detail. But before we get into all of that, let me go ahead and quickly introduce myself. My name is John. I'm the founder of TabletClass Math, and you guessed it, I'm also a middle and high school math teacher. And over many years, I've constructed what I like to believe is one of the best online video-based math help programs there is. So whether you need to take a full math course or you need help with the current course that you're in, my program can help you. I'll let you be the judge of it if you're interested. I'm going to leave a link to in the description of this video. Also, as a math teacher, I must emphasize the importance of taking notes, right? Those students who have the best notes typically have the best math grades, and the reverse is true. So take a look at your notes and ask yourself, hey, are these notes the best I can do? If they're not, you need to improve. But in the meantime, you need something to study from, and I actually offer very detailed, comprehensive math notes. I'm going to leave a link to those in the description of this video. Those would include pre-algebra, algebra 1, geometry, algebra 2, and trigonometry. Okay, so let's get into some big picture concepts of polynomials. So now, before I get into these big picture things, just real quick, right? What are some of the building blocks of polynomials? So, again, here we have like 2x, right? That's just like, well, that's just 2x. That's, we start learning things like that in algebra. There's a variable, but this is a polynomial. This is a type of polynomial. This is a monomial, okay? And we know that this is the coefficient, this is the variable, and this is a term. Okay, so I can have 2x plus 7, that's a binomial. Then I can have like 2x squared plus 7x plus 6, that's a trinomial. All these are polynomials, okay? And polynomials, the definition of a polynomial is that our variable, and let me just do this real quick. If we have a variable or variables, let's take our 2x to the 6 here, okay? The deal is that the power, okay, the power to the variable has to be 0, it has to be um, whole numbers, okay? So in other words, it's got to be 0, 1, 2, 3, all the positive integers and 0, okay? We can't have a decimal or a fraction up there. Anything that's not an integer, a positive integer value or 0, okay, as a exponent to a variable is something else. It's not a polynomial. Now, our coefficient, the number in front of the x, can be any real number, all right? So anything on the number line, a fraction, a decimal, irrational number, doesn't make a difference. We're good with that, right? The deal here, oftentimes what confuses students, is the power or the exponent to a variable or variables has to be these guys here, okay? So when we use that word polynomials, you need to know the definitions of these things, and they're extremely important and widely used in math. And in high school level mathematics, or even middle and high school level mathematics, you learn a lot about polynomials. Okay, so now And we just did that quick review. Here I have like a basic graph, and this could be a nice graph of a polynomial. So let's talk about the graphs of polynomials. And the graphs of polynomials are going to be primarily smooth and continuous. All right, smooth and continuous, something like this, meaning they're not going to do this deal. That's not smooth. All right, smooth is like, woo, nice like a roller coaster, right? And continuous, meaning that they're not going to go like this and then they're going to like go like that. There's a break. Okay, that's not a polynomial. Again, polynomial, smooth and continuous. All right. Now, we really like this in mathematics. I'm going to get to some of the reasons why. Now, let's take a polynomial like this. We'll just, I'll write this as a function, right? Let's say f of x equals, oh, I don't know, 4x cubed plus 2x squared minus x plus 6. I'm just making something up here. So don't get tied up in the specifics of this problem, all right? Now, here is a polynomial. I know, because I could see, right, we talked about the definition of a polynomial. So I know it's the graph of this polynomial is going to be smooth and continuous, but if I look at the highest power of this polynomial, it is 3, okay? So when you look at the degree of a polynomial, there's something interesting about that, because what this will tell us, this little 3, if we subtract 1 from it, the degree minus 1 is equal to 2. Okay, obviously, right? 3 minus 1. Specifically, you always subtract 1. So if this was like a 5th degree, it would be 5 minus 1. This is a 3rd degree, so it's 3 minus 1. So it's 2. So what that tells us is that this polynomial will have no more than 2 turns. Okay, so the graph will have no more than 2 turns. So you can see here, this has 1 turn and this has another turn. All right, so this could be, this graph here could possibly represent this particular polynomial, all right? So when you look at polynomials, you could say, all right, if the graph of this guy here will have no more than 2 turns. In other words, this graph will not do this, all right? That's a bad example. It won't do like this, all right? Because this is 1, 2, 3 turns. This graph can never be the graph of this polynomial, okay? So just something interesting, that a connection that you need to know about the graphs of polynomial. Smooth and continuous, and the amount of turns, excuse me. Now also, if this coefficient here is positive, you're going to, its behavior from left to right is going to be this way. It's going to be upward from left to right. So again, I don't want to get into all the little tiny details about the graphs of polynomial, but these are some of the big picture ideas. So when you're looking at this, you can be like, okay, no more than 2 turns. As if I said, hey, produce the graph, or sketch the graph of this, you can get some clues to it, because graphs are very valuable for us in mathematics, especially when we're trying to solve equations, right? So some things about the graph that you need to, graphs of polynomials that you need to appreciate. So real quick though, let's just look at this example in terms of a quadratic equation, right? So something like 2x squared plus x plus 1. So we know that the highest power of this polynomial is 2, okay? So automatically, hopefully you're at the level of mathematics to know that this is a quadratic equation. You're like, oh, that's a quadratic equation, not a parabola. No, quadratic equations are types or second degree polynomials. Okay, so this is a polynomial. So how many turns does this graph have? So quadratic equations, hopefully you know that the graphs of these guys are parabolas. Okay, so they go like this or like this. Now, how many turns does a parabola have? Well, it just have 1 turn, right? So if I look at that 2, and I go, oh, that's 2 minus 1, or 1, well, there you go, right? So the graph will have no more than 1 turn, and we can, kind of just reinforce that concept of the amount of turns in a parabola. All right, so maybe you knew that, maybe you didn't, but there you go, right? So we're just hitting some big picture highlights on things. Now, let's move on to this next thing, all right? FTA. So what is this? This is the fundamental theorem of algebra. The fundamental theorem of algebra, and this is really, really important. It kind of goes by different names, but typically, oftentimes it's described as the fundamental theorem of algebra. So let me draw something here. Let's say 2x to the fourth minus 7x cubed plus x squared minus x plus 9. Okay, so this is a parabola, obviously. I mean, not a parabola, excuse me. It's a polynomial. It's a what degree polynomial? It's a fourth degree polynomial. That's the highest power, okay? Highest degree, highest power of a polynomial when it's written in standard form, highest to lowest power. So the fundamental theorem of algebra basically states this. If you have a polynomial, okay, the polynomial, whatever the degree is, all right, in this case it's a fourth degree polynomial, okay, is how many solutions this polynomial will have, all right? This is very, very critically important when we're talking about polynomials, right? So we have a fourth degree polynomial, so this polynomial will have 4 solutions, okay? It's fourth degree, so we will have 4 solutions. Now, what type of solutions? Well, I'm talking about if you were to solve this polynomial, okay? Solve this polynomial equation, meaning we would do this, we would set this equal to 0, okay? We'd set this equal to 0, and we want to solve for x. So that's what I'm talking about here, okay? So if I wanted to do this, right, the fundamental theorem of algebra states that whatever the degree is, that's how many solutions we're going to have. So here we're going to have 4 solutions. Now, what type of solutions? Well, that's a whole nother different deal. We can have a combination, we can have all real number solutions, or we can have complex number solutions, imaginary solutions, or we can have a combination of both. So in more advanced algebra, depending on where you're at, we're going to go, look for these solutions. Okay, I'm like, oh, there's absolutely 4 solutions, no doubt about it. Now I have to, go look for these guys, and that's why having a graph is so important. So again, the fundamental theorem of algebra is going to be the degree, the highest power is the amount of the number of solutions you're going to have in a polynomial. Okay. All right, so that brings me to my next little topic here, and that's the roots, okay? There's different words for this: roots, solutions, zeros, okay, real number roots. But what I'm really kind of emphasizing here is this. Let's suppose I have some polynomial, okay, and this is the graph of the polynomial. All right, let's take this one for example. The x-intercepts, the points here that the graph crosses the x-axis, are real roots. So let's say this guy right here was -5, and this one here is at 3, and this one here is at 7. Okay, I said this is the graph of a third degree polynomial. What is the polynomial? Okay, well, how many real roots does this polynomial have? Well, we're looking at them, okay? These are the solutions. Anytime the graph of a polynomial crosses the x-axis, that is a real number root. So I could say, okay, -5 is a root, so I can write that as a linear factor as x plus 5. And then this one right here, I can write as x minus 3. And this one I can write as x minus 7 equals 0. Because if I set each one of these factors equal to 0, I would get x plus 5 is equal to 0, getting the solution x equals -5. X minus 3 is equal to 0, I would get the solution x equals 3. And here x minus 7 is equal to 0, I would get the solution x equals 7, right? Because we're kind of following this zero product property. I'm saying something, okay, this thing times this thing times this thing is equal to 0, all right? So I'm saying, hey, I got a bunch of things, I want to multiply them together, it's equal to 0. What does that tell me about these things, all right? Well, one or all of them have to be 0, right? You can't get a 0 when you're doing multiplication. This has to be 0, or all of these has to be 0. So this is an example of the zero product property, all right? So I can reconstruct this polynomial, okay? If I said this is a third degree polynomial, I'm like, oh, I have all my solutions, so I would just multiply all these together and I can actually get the polynomial. Okay, that's why the connection between the graph and the solutions are so important. But let's suppose for a second that I said this is the graph of a fifth degree polynomial. Okay, here's the graph of a fifth degree, the entire graph of the fifth degree polynomial. Now what do I do? Well, now this is a different situation. So I would say, okay, I have real number roots at -5, 3, and 7, but if it's a fifth degree polynomial, I'm missing two solutions. And so I can't have any more real roots here because this graph is not going to cross through. Now, if it's a fifth degree polynomial, remember that's something like x to the fifth plus 4x to the fourth, whatever the case is. So you might be saying, well, a fifth degree is 5 minus 1. I should have 4 turns. No, this is the maximum number of turns you're going to have. Okay, the maximum. In other words, a fifth degree polynomial will have no more than 4 turns. Okay, excuse me. So we have to ask ourselves, well, where are the rest of the solutions here? Well, those would be our little complex or imaginary solutions. Okay, so that could be a whole different deal. Some things that could be like plus or minus 2i, etc. Again, I'm not going to get into all of the techniques here that we use, and there's a lot of different various techniques that we have, and other additional theorems that we know about polynomials about roots. And those would include the rational root theorem, which is an awesome theorem. Then we can use different things like synthetic division, etc., etc. So again, polynomials, we know a lot about finding out where their solutions are at. So we use the graph, we use additional theorems, we use the fundamental theorem algebra, and we can go hunt these things down. They're really, really excellent stuff. Okay. All right, so again, we know a lot about polynomials. And that brings me to my last little thing I want to highlight, and I'm probably missing a few other more important highlights that I'm not putting in here, but just think big picture things that kind of come to mind. So this here is calculus, okay? So in calculus, we love polynomials because they're smooth and continuous, and it's easy to find like what we call the integrals. Okay, so let's say, in other words, to integrate polynomials. So for example, let's say I have 2x to the fourth plus 3x squared minus x plus 9. And let's say this polynomial function, okay, let's just say this is the graph of this polynomial function. Okay, let's suppose that's the case. Now, if I wanted to find the area of this, I'm really making some major oversimplifications here. Okay, so a matter of fact, it's not technically going to be even being correct, but I'm not worried about that. I'm just making a big point here. So let's say here's -7 on the graph right there, and here let's call this 5. Okay, if I wanted to find the area underneath the curves here, I can do what they call integration of this function. Now let's say this polynomial function describes this nice curve, right? This curve is smooth and continuous, so I would integrate, okay, which basically means find the area underneath the curve bounded by the x-axis here, and that would start from -7 and go to 5, and then I would plug in, I would put my nice little polynomial here, 2x to the fourth plus 3x squared minus x plus 9. So in calculus, to do this math, okay, to find the integral, all right, and do this calculation, it's really, really easy to do when we're dealing with polynomials. Okay, so polynomials, we love polynomials in calculus because we know that graphs are smooth and continuous. We know a lot about it, and it's easy to do our calculus stuff, whether it be derivatives or integration. So let's kind of take this a step further. I'm going to erase all of this. So let's suppose, I'm an aircraft designer. I'm just going to draw something here, and I'm trying to design an airfoil. So an airfoil would be like the shape of a wing, right? So here's an airplane. So here it's like this, right? And the airfoil is this shape right here on the side. So let's say it's like this. All right, let's say my airfoil's like that, all right, or maybe like this. Okay, something like that. Now, it's some sort of curve. It appears to be smooth and continuous, but let's say I want to describe a function, okay, that describes this curve, that models this curve. So there's a lot of different things that we can kind of try to match this curve up, okay, and this is a whole nother more advanced mathematics to try to find a function of something. Kind of gets into this thing called differential equations. Again, more advanced kind of stuff, but you'll get the main idea here. Is if I'm trying to find a nice function that describes precisely this curve, if I can get that to be a polynomial, or if I can find a polynomial that describes this, even though it continues on this way, doesn't, I don't worry about that. I just need what's going on between this location and this location. But if I could find a function, a polynomial function precisely that describes this, that gives me a lot of advantages. Um, when I'm doing more advanced math like calculus and engineering type of problems, etc. Okay, so if I got to do use more sophisticated mathematical modeling, well, then it is what it is, right? I got to do what I have to do. But if we can use polynomials, we can find polynomials. We love them because they're easy to work with. Okay, and that's why we study them so heavily at the kind of basic level or pre-calculus level mathematics. Okay, whether that be, you start off in middle school, but especially in high school, you don't even realize how much you are studying polynomials. There's you know, probably, I don't even know, maybe a quarter, a third of what you're studying has to do with polynomials, right? Huge, huge topic in mathematics. So hopefully this was insightful, okay? And maybe you didn't know some of these concepts, but if you didn't know it, don't worry about it. At least you have a good impression of what you will be studying, all right? But just really have a real appreciation of polynomials and how important they are and will be if you continue to study mathematics, which I hope you do. So if you liked this video in some way, enjoyed it, or learned something from it, please consider smashing that like button. And if you're new to my YouTube channel, please consider becoming a subscriber. I already have hundreds and hundreds of videos on my channel, been on YouTube for 10 plus years. All those videos are there for you. But I post new stuff all the time, okay? But if you really want my best resources, math help, you just follow the links in the description of this video. All right, so with that being said, I definitely wish you all the best in your mathematics adventures. Thank you for your time and have a great day.